morning, everyone. My name is Keith Bourne. I'm an automation researcher here at CCAM, and I'm here to talk about project G133, Task 4, which is basically robot puppet control for teleoperation of industrial robots. So we've found that there are several potential applications for controlling industrial robots via teleoperation. And we've previously explored this using a haptic pen type device. So this is a small device where you hold a stylus and you can move it to move the tool center point of the robot and get some level of force feedback. We found that this has worked really good for local position control, but it's not as good for gross motions of the robot in which you're moving beyond an area that you would want to just use a simple linear move. It also lacks the intuitive feel for the physical limits of the robot joints that you need to do good smooth motion. We also found that precise force control wasn't always necessary, well, precise force feedback to the user. So what we investigated was a simple puppet control device shown on the upper right of the screen, in which we have a kinematically identical controller to the robot. So such a controller would have to allow a smooth one-to-one mapping of the configuration of the controller to the robot, and it would have to allow for safely accounting for situations where you start it up and the controller does not match the robot, because this is not a power device. This is a very simple position measurement based controller. This controller can either be full-sized or it can be a scaled model, either smaller than your robot if your robot is large, or larger than your robot if your robot is very small. It can be constructed from modular components fairly inexpensively, and it might incorporate some level of haptic feedback, such as vibration motors, if that is required. So the test bed that we constructed was a 75% scale model of a UR5 robot shown on the upper left of the screen. And what we actually did was we took the CAD model of the robot, and right on top of that we built the assembly of the robot puppet. So it is perfectly scaled, and all the revolute joints are at the same locations that they would be on the robot. We also constructed 6 identical joint modules with 14-bit absolute encoders shown in the bottom center of the screen. Each of these modules actually had a pinned mechanism, which you can see at the lower left, center, and right, that allowed the joint to be turned through plus or minus 340 degrees of motion, and then you would hit a stop. This is compared to the plus or minus 360 degree motion per joint that the actual robot has. We also had a toggle switch located on the handle of the robot to open and close the handle of the puppet, to open and close the gripper of the robot, and a foot pedal not shown, which was used to actually make the robot start mimicking the puppet, so it wouldn't have to at all times. So this entire unit cost only about $2,000 to build. So during operation, what happens is that the foot pedal, all of the encoder joint values, the gripper switch value, and the actual position of the real robot joints are fed into a single board computer that is continuously running a control logic loop. The way this works is that when you push on the foot pedal, this sends an enable signal to the robot controller, which tells it, until I let up on this foot pedal, move to the joint angles that I tell you continuously at a rate of 125 hertz. The single board computer is smart enough to look at the difference between the joint angles of the puppet and the joint angles of the robot, and if those values are quite large, it will significantly slow down the motion of the robot until the two joints get in sync, and then they'll move at a significantly faster rate. So basically, as you initially push down the pedal, the robot will gently approach the position of the puppet, and then it will perfectly mimic its motion, including opening and closing the gripper. We also have some logic incorporated to avoid the robot having any sort of strange behavior if there's a loss in communications or one of the encoders glitch out. So to test this out, we set up a simple test bed where we had several objects positioned around a UR5 robot with a gripper, with an operator positioned about 5 feet away, and the puppet oriented identically to the robot. We found that we could readily control this robot through use of the puppet throughout its entire range of motion. It was quite intuitive, actually, and yet it was sensitive enough that we were able to insert 6 millimeter diameter bolts in 8 millimeter slots and some extrusion on the table. To test out the basically user-friendliness of the system, we brought in several volunteer users and gave each of them about 1 minute of training on how to use the piece of equipment. After about 1 minute, each of the users was easily able to perform pick-and-place tasks, to stack objects, and even to do insertion of objects, such as the bolt being inserted into the hole, which you can see in the video. Additionally, we were able to easily move throughout the full range of motion, as also shown in the video here. Both activities that actually would take some effort to program by hand. The primary limitation ended up being that the user was standing about 5 feet from the robot, so your control was very much dependent upon your eyesight. So, at least in my own case, that somewhat limited my ability to do precise motions. In a real teleoperation setup, there'd be cameras, perhaps 2D or 3D, positioned to render that a moot point. So we're actually proposing, based upon how promising the system is, to extend it in the future such that you have remote control of the system over a network. So you could be in a different room from the system, communicating via Ethernet. There's not much data that needs to go back and forth, after all. Visual feedback could be added, such as 3D monitors or 3D goggles, and limited haptic feedback, such as vibration of the robot when you're contacting vibration of puppet when a robot contacts something, could also be added. Improved display of data and the addition of canned routines to do simple repeated actions like changing out a gripper, changing out a tool, could also be added to the system to make it a fairly effective teleoperation rig.